Okay, so we just finished the chapter on gases, so now we're on chapter 10, which is liquids and solids. And similarly to how we were thinking about gases, it's really important that we think about physical states in terms of the particles that make them up. So the primary thing that is going to influence whether we think of something as a solid, a liquid, or a gas is based on the amount of space that separates the particles. And so those lead to various physical properties, which presumably you already know about. So gases are more fluid. The particles move past one another very easily. They're highly compressible. And then liquids are a little bit less so. The particles are a little bit closer together. They're still fluid, but they're not able to be compressed. So liquids have a definite volume. And then solids, of course, have very tightly packed particles, and their particles, in terms of movement, are confined to just vibrations. And so we're just thinking about how gases have much more freely moving particles, liquids less so, and then solids are much more compacted, okay? If we're thinking about phase changes, a substance can go from being a solid to a liquid to a gas, or vice versa, depending on the temperature and pressure at which the substance finds itself. Okay, and so there are two ways that we're going to think about representing the changes. Okay, and so that's going to be through a heating curve, and we'll just look at heating curves, although heating and cooling curves work in a similar way, and I'll point that out when we get to that, and then we'll also look at phase diagrams, okay? And so these are different ways of representing a substance changing from a solid to a liquid to a gas. Okay, so on the next page, this is a heating curve, and it's called a heating curve because we start out with our substance in the solid state, okay, and then we end with it in a gaseous state. If it were a cooling curve, it would be the opposite. So it would start as a gas, and it would go to a solid, and so you'd see a decline in this curve here. So what this represents is that as we add heat energy, okay, that creates a change in the physical state. Okay, so you can see that heat is on the x-axis, temperature is on the y-axis. They're closely related. So we're assuming that pressure is constant here. And so we start out with our substance as a solid, and as the heat and temperature increases, that solid is going to get hotter and hotter. And so it's still a solid, but the temperature is increasing until it reaches the melting point. Okay, so at the melting point, that is the temperature at which, okay, we can transform from a solid to a liquid. So at the melting point, we actually have solid and liquid existing simultaneously. They're at equilibrium. Once we exceed that melting point, okay, so if we add a little bit more heat, okay, or the temperature increases, then our substance is entirely liquid. And so we can start heating this liquid up. That's what we see along this line, is we're heating the liquid up until we reach, so this is still liquid, until we reach the boiling point. Okay, at the boiling point, our liquid and gas exist at equilibrium. Okay, and then once we exceed that boiling point, we are just heating the gas up. Okay. So one of the important things to keep in mind here that is probably already apparent to you based on what we talked about in terms of the movement of particles and how far they are separated from one another is that solids have the least amount of energy. Okay, so their particles are moving around the least. They're associated with lower temperatures. Okay, and then liquids have a little bit more energy, and then gases have the most energy. So if you're talking about diminishing the energy of a substance, that means you're going from gas to a liquid or liquid to a solid. Okay, and then down at the bottom of the page, just some terminology you need to be familiar with. Another name for the melting point is the heat of fusion. Okay, so that's the temperature at which a solid goes to a liquid, and then the heat of vaporization is the same thing as boiling point. So that's associated with the transition from a liquid to a gas. Okay, so if you'll scroll down, the next way that we can represent phase changes is by looking at a phase diagram. And this actually gives us a little bit more information because if you notice, we have pressure on the y-axis and then temperature on the x-axis. So various intensities of pressure or temperature correspond with different states of matter, and you can look at, at some given temperature, at some given pressure, is this substance existing as a solid or a liquid or a gas, okay? The other information that we can determine from a phase diagram is that you can look at the slope of this solid liquid line, and depending on whether it is a positive slope or a negative slope, that tells you about the relative density of the solid versus the liquid. So if that line has a negative slope, okay, so in other words, if it is in that direction, okay, that means that the solid is less dense than the liquid state of the substance, okay? So water would be an example of that, okay? If you see that that line has a positive slope, like it is in the example that's given, that means the opposite, that the solid is more dense than the liquid, okay? So under conditions of high pressure and then of low temperature, under conditions of high pressure and low temperature, that's going to favor a solid state, and then low pressure and high temperature is going to favor a gaseous state, and then intermediate is going to favor a liquid state. So remember, the horizontal lines on the heating curve represented equilibrium of solid and liquid and gas. So same thing here. So the lines that separate any different states, so like this line here, if the substance has, a point along this line, so it's some temperature and pressure, that means that it is at equilibrium of those two mixtures. Okay, so same for this line. So at any point along this line, the substance is at equilibrium in the liquid and gas state. Okay, and then solid and gas also has an equilibrium line. So that's one thing that's a little bit different when we're considering pressure and not just temperature. At the triple point, okay, so the point at which the solid, liquid, and gas lines meet, all three phases are at equilibrium. Okay, and then the final piece that you need to be concerned with is the critical point, and that just represents, okay, if you exceed a temperature or pressure beyond this point, okay, that means that your substance can no longer exist as a liquid. In other words, it has to exist as a gas. So if we imagine extending this liquid gas line up beyond the phase diagram, you can see that everything beyond this point would be a gas. Okay, so that's what the critical point is. Once you exceed that point, your substance can no longer exist as a liquid. Okay, so you can think of it as sort of the end point in terms of pressure and temperature. So we can think about for this point, this pressure that corresponds with this point is considered the critical pressure, and this temperature here at the end of our graph is considered the critical temperature, and those all correspond with the critical point. And then the other thing that you need to be familiar with for this chapter is the name of different phase changes. So for instance, solid to a liquid is called melting, liquid to a solid is called freezing, and so on. So you need to essentially memorize the names of all of these phase changes. Okay. If you look at the next page, it basically associates these same vocabulary terms looking at a phase diagram. So for instance, if you're told that a substance starts out at a particular temperature and pressure, okay, so let's say it corresponds to these points. If it starts out as a liquid, and then let's say I lower the pressure, but the temperature stays the same. So now the point is down here. you should be able to identify that change. So we're going from a liquid to a gas is called what? And so it would be called vaporization. So liquid to a gas is vaporization. So you're basically just using graph skills and associating them with the vocabulary terms for different phase changes. And so if you're comfortable doing that, then you're basically fine answering phase change questions for this chapter. Okay, so this is looking at how the phase diagram of carbon dioxide differs from that of the phase diagram of water. One thing you should notice is that these essentially look the same. We still have pressure on the y-axis, temperature on the x-axis, and so on. They have the same basic structure. So you should be comfortable drawing this sort of Y shape and knowing that solid is on the left, liquid is in the middle, and then gas is in the bottom right. One thing that's different is obviously that this line here, this solid liquid line, has different slope for water than it does for carbon dioxide, which makes sense given what we've already talked about. Okay. So let's look at this in class problem. So compare what happens in general to the energy, order, and spacing of particles when a solid changes to a liquid, and with what happens to the energy, order, and spacing of the particles when gas changes to a liquid. So solid to liquid, and then gas to liquid. Okay? And so your answer should simply be that as we go from solid to a liquid, the energy should increase, the order should decrease, and the spacing should increase. Okay, so for gas to a liquid, our energy of our particles decreases, our order increases, and the spacing decreases. Okay, so make sure that you understand the differences between those. Okay, so now we start getting into intermolecular forces. And the main intermolecular forces that we'll talk about are listed here. So hydrogen bonding, dipole-dipole, and London dispersion. Hydrogen bonds are actually the strongest, then dipole-dipole, and then London dispersion. Okay, so we've already talked about intramolecular forces this year. Remember, those are listed down below. So intramolecular are ionic, polar covalent, and nonpolar covalent bonds, and those are listed in order of their strength. Okay, so remember, intramolecular were bonds within a particular molecule. Intermolecular, inter in Latin means between. So these are the bonds that exist between molecules. Okay, so one important thing to keep in mind here is that when we are changing phases, so in other words, when I go from a solid to a liquid, okay, I am not breaking bonds within molecules. I'm breaking bonds between them. Okay, so let's say I'm boiling water, so I'm going from a liquid to a gas. Okay, I have hydrogen bonds, and we'll talk about how I know that they're hydrogen bonds, okay, in a little bit. So this bond within my water molecule is a polar covalent bond. Okay, that is not breaking when I'm boiling water. What is breaking is that bond right there. That's my hydrogen bond that exists between my water molecules. Okay, so that is what makes, for instance, when water boils and I'm turning into a gas, the particles are separating more, and that is why, because they're not linked together with their hydrogen bonds as much as they had been previously. Similarly, if I'm going in the opposite direction, so let's say liquid to a solid, I am forming these hydrogen bonds by virtue of having more order. Okay, so if I'm going from a solid to a liquid to a gas, I am breaking intermolecular bonds. Okay, and then if I'm going in reverse, so gas to a liquid to a solid, I am forming intermolecular bonds.